Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module we are discussing types of hybridization. The contents of this module are hybridization, types of hybridization in normal molecules and ions, type of hybridization in coordination compounds, hybridization and geometry, determination of hybridization from molecular formula. First of all, hybridization. Hybridization, as we know, it is defined as the process of intermixing of orbitals of slightly different energies resulting in the formation of new set of orbitals of equivalent energies and shape. That means during hybridization, a group of orbitals will merge together, mix together, combine together to produce a set of orbitals, a set of identical orbitals. Identical means identical in energy and in shape. For example, when one 2s and 2p orbitals, 3 2p orbitals of a carbon hybridize, there occur the formation of 4 new sp3 hybrid orbitals. This hybridization is very popular in CH4 molecule. You can take a CH4 molecule as an example to illustrate sp3 hybridization. In sp3 hybridization, in CH4 molecule, the central atom carbon shows sp3 hybridization, and for that, one 2s orbital and 3 2p orbital take part, and as a result of the mixing, 4 sp3 hybrid orbitals are produced on the central atom carbon, and these 4 sp3 hybrid orbitals are having identical energy and shape, and they prefer to have the tetrahedral geometry. This basic concept you have learned in the previous module, and this part is just taking for recalling the concept of hybridization. Now, this is the illustration of sp3 hybridization. Here you can see the combination of one s orbital and 3p orbital to produce 4 sp3 hybrid orbitals, which are arranged to the 4 corners of a tetrahedron with a bond angle of 109.5 degree. Now, the main features of hybridization are familiar to you, and these are the important salient features of hybridization. The number of hybrid orbitals is equal to number of atomic orbitals that get hybridized. The hybrid orbitals are always equivalent in energy as well as shape. And the third salient feature is that the hybrid orbitals are more effective in forming stable bonds than pure atomic orbitals. These hybrid orbitals are directed in space in some specified or some preferred directions to have minimum repulsion between electron pairs and thus a stable arrangement. From this point, it is very well clear that for a particular hybridization there is a definite geometry. That means a particular hybridization determines the geometry of a molecule. The type of hybridization indicates the geometry of the molecule, and this is the correlation between the type of hybridization and the geometry of the molecule. So, the chart represents hybridization in the first column and geometry in the second column. It is very well clear that sp hybridization implies linear geometry, sp2 hybridization leads to trigonal planar geometry, sp3 hybridization leads to tetrahedral geometry, sp3d hybridization leads to trigonal bipyramidal geometry, and finally sp3d2 hybridization leads to the octahedral geometry. So, hybridization has a close connection with the geometry of the molecule, or the geometry of a molecule is determined by the hybridization. Now, we are discussing some important conditions for hybridization, and these are the important conditions for hybridization. The orbitals present in the valence shell of the atom are undergoing hybridization. Only orbitals of the valence shell will undergo hybridization. That is the most important condition. And the second one, the orbitals undergoing hybridization should have almost equal energy. That is, huge energy difference between atomic orbitals will not lead to effective hybridization. This is the third condition for hybridization. Promotion of electron is not essential condition prior to hybridization. That means electronic excitation is not a mandatory condition, is not a necessary condition for prior to the hybridization. It is not necessary that the only half-filled orbitals participate in hybridization, and in some cases even filled orbitals of the valence shell can also take part in hybridization. In certain rare cases, for example in coordination complexes, vacant orbitals can also undergo hybridization, and these are various important conditions for the hybridization. Now we are discussing type of hybridization present in normal molecules and ions. Hybridization is classified based on the type and number of atomic orbitals involved. Each type results in a specific geometry and bond angles that determine the shape of molecules. Let us now have an overview on different common hybridizations in normal molecules and ions. It should be noted that the hybridization shown by coordination complexes is different from that of normal molecules. That's why in this module we can have a discussion in two parts. The first part, the hybridization shown by normal molecules and ions, and in another part we will discuss the hybridization shown by coordination complexes. First of all, hybridization shown by normal molecules, out of which we are dealing sp hybridization first. The sp hybridization involves the mixing of one s and one p orbital, resulting in the formation of two equivalent sp hybrid orbitals. The suitable orbital for sp hybridization are s and pz if the hybrid orbitals are to lie along the z-axis, and in many cases z-axis is taken as the molecular axis, and in order to have an end-to-end overlap between s and pz orbital is most apt. So in sp hybridization it is generally occur between s orbital and a pz orbital. The two sp hybrid orbitals or sp hybrids point in the opposite direction along the z-axis, yielding linear geometry to the molecule with a bond angle of 180 degree. There are so many examples for molecules having sp hybridization. The popular examples include beryllium chloride, carbon dioxide, ethane or acetylene C2H2. Example of ions showing sp hybridization are here. Cyanide ion, that is Cn minus ion, nitronium ion or NO2 plus ion are two ions that exhibit sp hybridization. Now we are illustrating sp hybridization in acetylene molecule. Acetylene molecule is CH triple bond CH. This is the central atom carbon. The central atom carbon has a ground state electronic configuration of 1s2, 2s2, 2p2, and out of this the valence shell electrons, valence shell orbitals will take part in hybridization. So one of the electron present in the 2s orbital is excited to the 2p orbital. So you are getting an excited state electronic arrangement like this. This is 2s, 2px1, 2py1 and 2pz1. Out of these four half-filled orbitals, one s orbital and one p orbital undergo hybridization. That is, you are getting sp hybridization. So as a result, two sp hybrid orbitals are produced. Remember, there are two unhybridized half-filled p orbitals are also present in central atom carbon of acetylene, each carbon of acetylene. Now, during the formation of acetylene molecule, the sp hybrid orbital overlap with another sp hybrid orbital of carbon to form a sigma bond, and remaining one sp hybrid orbital on each carbon overlap with the 1s orbital of hydrogen to form CH sigma bond. So in C2H2 there are two CH sigma bonds, one carbon-carbon sigma bond. So there is a total of 3 sigma bond. You can see two unhybridized p orbitals in carbon atom. They are 2py and 2pz orbitals. These two orbitals undergo lateral overlap to produce two pi bonds. Thus, in the molecule acetylene, there are two pi bonds and 3 sigma bonds. Among 3 sigma bonds, 1 sigma bond is between two carbon atoms and 2 sigma bond is between carbon and hydrogen. Now we are discussing the second popular type of hybridization that is present in simple molecules and ions, that is nothing but sp2 hybridization. In this type of hybridization, there is the involvement of one s and two p orbitals in order to form three equivalent sp2 hybrid orbitals. The geometry of the molecule or the geometry that generates from sp2 hybridization is trigonal planar geometry. The bond angle is equal to 120 degree, and examples of molecules showing sp2 hybridization are here: BF3 molecule, ethene or C2H4 molecule, and SO3. There are some ions also exhibit sp2 hybridization, and they involve carbonate ion, that is CO3 2-, nitrate ion NO3-. So carbonate ion and nitrate ion are ions that depict sp2 hybridization. Now we can illustrate sp2 hybridization in ethene as a reference example. So this is the carbon atom in the ground state arrangement. During the formation of C2H4 molecule, there occur an electronic excitation, and this electronic excitation leads to 4 half-filled orbitals, half-filled s orbital and 3 half-filled p orbitals. Out of this, 1 half-filled s orbital and 2 half-filled p orbital undergo hybridization to produce, sp2 hybridization to produce 3 sp2 hybrid orbitals, and these 3 sp2 hybrid orbitals leads to generation of C2H4 molecule as depicted here. There are 3 sp2 hybrid orbital on each carbon atom. Out of these 3 orbitals, one of them combine together to form a carbon-carbon single bond. 2 remaining sp2 hybrid orbitals overlap with 1s orbital of hydrogen to form CH bonds. So in C2H4 there are 4 CH bonds and 1 carbon-carbon sigma bond. In addition to this, you can see the presence of 1 hybridized half-filled p orbital on each carbon. They will undergo lateral overlap to produce a pi bond. So on a sum, in C2H4 molecule, there occur the formation of 5 sigma bonds and 1 pi bond. This about the structure of ethene. There are 5 sigma bonds and 1 pi bond. This is 1 pi bond, this is a sigma bond, this is another sigma, this is sigma bond, and sigma bond. So in C2H4 molecule, you can see 4 plus 1, that is 5 sigma bonds and 1 pi bond. Now we are entering into another popular hybridization, that is nothing but sp3 hybridization. The 4 sp3 hybrid orbitals so formed are directed towards 4 corners of a regular tetrahedron. That is, it is clear that in sp3 hybridization, there are 4 orbitals that take part in hybridization and 4 sp3 hybrid orbitals are produced. These 4 sp3 hybrid orbitals profess to have a stable tetrahedral arrangement, or the geometry is tetrahedron. The angle between sp3 hybrid orbital is fixed, that is equal to 109 degree 28 minutes, or simply 109.5 degree. There are so many examples for simple molecules with sp3 hybridization. The examples include methane, ammonia, water, ethane or C2H6. There are some ions also exhibit sp3 hybridization. The examples include ammonium ion, that is NH4+, sulfate ion SO4 2-. Now we can illustrate sp3 hybridization by taking water molecule as an example. In water molecule, the central atom oxygen is having ground state electronic configuration 2s2 2p4. Prior to the hybridization, there occur no electronic excitation. That I told you the fact that electronic excitation prior to the hybridization is not necessary. So here you can see the presence of 2 lone pairs and 2 half-filled orbitals. But these orbitals are different in energy, so they will undergo mixing up to produce 4 sp3 hybrid orbitals. Among the 4 sp3 hybrid orbitals, you can see that 2 of them are half-filled orbitals and 2 of them are lone pairs or filled orbitals. So these half-filled sp3 hybrid orbitals overlap with 1s orbital of 2 hydrogen atom to produce 2 OH bonds. That generates the water molecule. So in water molecule, the central atom oxygen has 2 lone pairs as depicted here and 2 bond pairs. So this molecule, if you are excluding these lone pairs, you will get a bent shape. If you are considering the lone pair also, then the geometry will be tetrahedral geometry with 2 positions occupied by lone pair. So from this example it is very well clear that geometry is different from shape. So in molecules with lone pair, shape is different from geometry or both are different. That is, in considering the shape of a molecule, you are ignoring the lone pair. However, for a particular hybridization, its geometry is constant. Since the central atom, oxygen, exhibit sp3 hybridization, the geometry of the molecule is tetrahedral. But two corners of the tetrahedra are occupied by lone pairs. So the correct geometry is tetrahedral with the two positions occupied by lone pair. If you are removing that lone pair, you will get a bent shape. So the shape of the molecule is bent and the geometry is constant, that is tetrahedral geometry. The sp3 hybridization in ethane is also taken here for an illustrative comparison with the ethene and acetylene that we have learned earlier. So in the case of ethane molecule, the central atom carbon depict sp3 hybridization. Carbon in the ground state is shown here with electronic arrangement, outer shell 2s2 2p2, and there occur an electronic excitation to produce a 4 half-filled orbital, out of which 3 are half-filled p orbitals and 1 is half-filled s orbital. These 4 half-filled orbitals undergo mixing up to produce 4 sp3 hybrid orbitals. So in 4 sp3 hybrid orbitals, all are half-filled, and these half-filled 4 sp3 hybrid orbitals overlap with the carbon and hydrogen atoms to produce the C2H6 molecule or ethane molecule. This is the overlapping picture that generates C2H6 molecule. Here there occur the overlapping, end-to-end overlapping between sp3 hybrid orbitals of each carbon to form a sigma bond. This represents a sigma bond, and the overlapping of sp3 hybrid orbital with the oneness of hydrogen also generate the sigma bond. So in C2H6 molecule or ethane molecule, there is no pi bond formation, there is no lateral overlap, all the bonds present here are sigma bonds. Now, another popular hybridization shown by simple molecules and ions is nothing but sp3d hybridization. The 5 sp3d hybrid orbitals so formed are directed towards the 5 corners of a trigonal bipyramid, yielding 2 bond angles. They are nothing but 90 degree and 120 degree. There are many examples for simple molecules with sp3 hybridization that involves PCl5, sulfur tetrafluoride, ClF3 or chlorine trifluoride. Some molecules are here. In addition to these molecules, there are some ions also, and the ions include ICl2 minus ion, I3 minus ion, etc. These ions also show sp3d hybridization of the central atom. We can illustrate sp3d hybridization in PCl5 molecule as a representative example. This is the ground state electronic configuration of phosphorus, where the electronic arrangement is 3s2, 3p3 and 3d0. You can see there are no electrons present in the d subshell. During excitation, one of the electron present in the 2s orbital just excited to the 3d orbital. So you are getting 5 half-filled orbital. The 3s orbital is now half-filled. 3p orbitals are already half-filled, and due to the promotion of an electron from 3s to 3d, the d orbital, one d orbital now also half-filled. So you are having 5 half-filled orbitals, and these 5 half-filled orbitals include 1 s orbital, 3p orbital and 1 d orbital. They will undergo mixing up together to produce 5 sp3 hybrid orbitals. These 5 sp3 hybrid half-filled orbitals overlap with the 2p z orbital, with the p z orbital of chlorine atom to produce the PCl5 molecule. So the PCl5 molecule can be represented like this. This molecule is having trigonal bipyramidal geometry as well as trigonal bipyramidal shape. The shape and geometry are same because there is no lone pair of electron on the central atom phosphorus. Now we are discussing another hybridization for common molecules and ions, that is nothing but sp3d2 hybridization. There are 6 sp3d2 hybrid orbitals are produced in this hybridization. The 6 sp3d2 hybrid orbitals so formed are directed towards the 6 corners of an octahedron, yielding a bond angle of 90 degree. The examples for molecules with sp3d2 hybridization are SF6 and XCF4. These are some molecules. In addition to this molecule, PCl6 minus ion is an ion that exhibit sp3d2 hybridization. We can illustrate the sp3d2 hybridization by taking XCF4 as an example. Here the central atom xenon has a ground state electronic configuration of 5s2, 5p6 and 5d0. There are no d electrons are present here in the ground state, and during the formation of HCl4 molecule, 2 electrons from the 5p orbitals excited to 5d orbital, leading to this electronic arrangement of 5s2, 5p4, 5d2. So, in this arrangement you can see the presence of 4 half-filled orbital and 2 completely filled orbital. On a sum you are having a total of 6 orbitals. These 6 orbitals, that is 1 s orbital, 3p orbital and 2d orbital, undergo hybridization to produce HCl4 molecule, that is the central atom exhibit sp3d2 hybridization. And you can see the presence of 2 lone pairs. These 2 lone pairs are present on the central atom itself. Excluding the contribution from the lone pair, there are only 4 bond pairs. So, this molecule has a square planar structure or square planar shape. Even though the geometry is octahedral, the shape is square planar. This is because there occur the existence of 2 lone pair of electrons on the central atom xenon. If there is lone pair of electron on the central atom, geometry will be different from shape. So, the shape of HCl4 molecule is square planar. The geometry of HCl4 molecule is octahedral with the 2 lone pairs. Now, we are discussing a consolidation of type of popular hybridizations exhibited by simple molecules and ions. This is about the consolidation. The first column shows the hybridization. Number of orbitals mixed are shown in the second column. Third column represents the number of hybrid orbital produced. Geometry is given in the fourth column and bond angle is shown in the last column. It is very well clear that sp hybridization leads to linear geometry with a bond angle of 180 degree. sp2 hybridization creates trigonal planar geometry with a bond angle of 120 degree. sp3 hybridization creates tetrahedral geometry with a bond angle of 0.5 degree. sp3d hybridization implies trigonal bipyramidal geometry with the 2 bond angles 90 degree and 120 degree. And finally, sp3d2 hybridization implies an octahedral geometry of bond angle 90 degree. We are discussing types of hybridization in coordination compounds. You are familiar with the coordination compounds where there exists a coordinate bond between metal and ligands. So, metal and ligand coordinate bond leads to the generation of different kind of coordination compounds. So, in coordination compounds, ligands donate a pair of electron and metal has to accommodate that electron. So, in metals there must be vacant orbitals. These vacant orbitals generally undergo hybridization. We can enter into more details of the hybridization shown by coordination complex here. Coordination complex exhibit different types of hybridization depending on the metal center, the nature of the ligands and the coordination number of the compound. For example, NiCO4 times exhibit sp3 hybridization. NiCN 4 times 2 minus exhibit dsp2 hybridization. FeH2 6 times 2 plus exhibit sp3d2 hybridization. So, it is very well clear that the hybridization depends on nature of the metal, nature of the ligand, coordination number of the molecule, etc. Now, according to valence bond theory of coordination compounds, the central metal make available empty orbitals to accommodate electrons from the ligand. When a coordination complex is produced, ligand donates its electrons to the central metal. In order to accommodate the electrons donated by the ligand, the central metal has to take vacant orbitals. And these vacant orbitals must have different energies. So, prior to the compound formation, these vacant orbitals with the different energies undergo mixing up to get a set of vacant orbitals having identical energy and shape. That's why the hybridization occurs in coordination compounds. These vacant orbitals undergo hybridization which determine the geometry of molecule and magnetic behavior like high spin, low spin, etc. So, in a coordination complex, during its formation, the central metal makes some available vacant orbitals. These vacant orbitals undergo hybridization. Hybridization determines geometry of the molecule and the nature of magnetic behavior of the molecule. Let us now have an overview on different common hybridizations in coordination compounds. First of all, sp3 hybridization. In sp3 hybridization, 4 vacant orbitals, preferably 1 s orbital and 3 p orbitals of the central metal undergo hybridization to yield 4 sp3 hybrid orbitals. This is shown by systems with the coordination number 4. The geometry will be tetrahedral and a typical example is NiCl4 2-. The sp3 hybridization in NiCl4 2- is discussed here. The orbitals of nickel 2+ ion in NiCl4 2-, the central atom nickel exhibit 2+ oxidation state. So, nickel is in nickel 2+ state. Nickel 2+ has an electronic arrangement in the ground state like 3d8 4s0 4p0 because nickel 2+ is a 3d8 system. And sp3 hybrid orbitals of nickel 2+ is shown here. This is because 1 s orbital and 4 p orbitals are empty now, and these 4 orbitals undergo equalization of their energy and shape, that is sp3 hybridization happens, and 4 sp3 hybrid orbitals are produced. That 4 sp3 hybrid orbitals are empty in nickel 2+ and electron pairs from each chloride ligand. There are 4 such chloride ligand will donate their electrons to the vacant sp3 hybrid orbitals to form NiCl4 2- molecule. This NiCl4 2- molecule have a tetrahedral geometry with a bond angle of 109 degree 28 minutes. Now we are discussing another hybridization shown by coordination complex, that is nothing but dsp2 hybridization. From the notation itself, it is very well clear that 1 d orbital, 1 s orbital and 2 p orbital take part in dsp2 hybridization. The 4 vacant orbitals participated here are 1d, 1s and 2p orbital. The central metal undergo hybridization to yield 4 dsp2 hybrid orbitals. Coordination number is also 4 here. The geometry will be different from sp3 hybridization, that is 4 molecules with the dsp2 hybridization, the geometry will be square planar. A typical example is shown here, NiCN4 times 2-. In NiCl4 2-, the hybridization is sp3, but in NiCN4 times 2-, the hybridization is dsp2. So, we are now discussing dsp2 hybridization in NiCN4 2-. The central atom nickel 2+ ion has a ground state configuration 3d8 4s0 4p0, and for the sake of dsp2 hybridization, the electrons, these 2 unpaired electrons are paired here, getting a configuration of 3d8, and 1 d orbital will be free. That d orbital merge with 1 s orbital and 2 p orbital to get 4 dsp2 hybrid orbitals. So, in nickel 2+ of NiCN4 times 2-, there are 4 vacant dsp2 hybrid orbitals. To these vacant dsp2 hybrid orbitals, electrons are donated by cyanide ions. They are ligands and lead to the formation of NiCN4 times 2-. This NiCN4 times 2- exhibit a square planar geometry as shown here, and the bond angle here is 90 degree. Now another hybridization shown by coordination complex, even though it is rare, we are discussing for the sake of convenience, that hybridization is dsp3 hybridization. Here 5 vacant orbitals, they are 1 d orbital, 1 s orbital and 3 p orbitals of the central metal undergo hybridization to yield 5 dsp3 hybrid orbitals. Here the coordination number is 5, geometry will be trigonal, bipyramidal, and typical example is iron pentacarbonyl FeCO5 times. We can discuss the hybridization, the dsp3 hybridization in FeCO5 times here itself. The central atom iron has a ground state configuration of 3d6 4s2, but there are no electrons in the 4p shell, and there occurs some arrangement, pairing of electrons happens to make 1 d orbital free, and the hybridization shown here is dsp3 hybridization. There are 5 vacant dsp3 hybrid orbitals. Electrons are donated by the carbon monoxide ligand to this vacant dsp3 hybrid orbitals to yield FeCO5 times, and FeCO5 times the molecules exhibit a trigonal bipyramidal geometry with 2 bond angles. In-plane bond angle is equal to 120 degree, other bond angle is 90 degree. Now another hybridization is sp3d2 hybridization. Here 6 vacant orbitals on S 3p orbital and 2 outer d orbitals of the central metal undergo hybridization to yield 6 sp3d2 hybrid orbitals. Coordination number of such molecule is equal to 6 and geometry is octahedral. Typical example is shown here, that is COF6 3-. We can illustrate the sp3d2 hybridization in COF6 3- molecule like this. The central atom is CO3 plus ion. It is having a ground state configuration of a 3D 6 4s0 4p0 and 4d0, and sp3d2 hybrid orbital CO3 plus are formed like this, and the hybridization occur by picking up 2 outer d orbitals, 3 4p orbitals and 1 4s orbital, giving a total of 6 orbitals. The 6 orbitals are 4s orbital, 3 4p orbital and 2 4d orbitals. The d orbitals are from outer shell. That's why we are representing sp3d2 hybridization. If the d orbitals are from inner shell, you can mark this hybridization as d2sp3. In the coming slide, we will discuss such kind of hybridization of also. So, in COF6 3-, there are 6 sp3d2 vacant hybrid orbital. To that, electrons are donated by the 6 fluoride ion ligands, yielding the formation of COF6 3-. This is the structure of the molecule. The structure is octahedral with a bond angle of 90 degree. Moving on to another type of hybridization, that is D2sp3 hybridization. Before entering into this, I am asking a very simple question. What is the difference between D2sp3 hybridization and sp3d2 hybridization? In both the case, the geometry will be same, bond angle will be same, 6 hybrid orbitals are also produced. Then what will be the difference? The difference is in such a way that in sp3d2 hybridization, the participating d orbitals are from outer shell. However, in D2sp3 hybridization, the participating d orbitals are from inner shell. So, an example for D2sp3 hybridization is there. We can illustrate, we can move on to that typical example by simply going through this concept. Here 6 vacant d orbitals, 2 inner d orbital. Look on this, 2 inner d orbitals are take part in hybridization, 1 s orbital and 3 p orbitals are take part in hybridization to undergo 6 D2sp3 hybrid orbitals. So, coordination number of the molecule is equal to 6 and the geometry will be same as sp3d2 hybridization, that is nothing but octahedral. The typical example is here CONH3 6 times 3 plus. We can illustrate D2sp3 hybridization by taking CONH3 6 times 3 plus as a typical example. Previously, we have discussed sp3d2 hybridization with respect to COF6 3-. Now, we are discussing D2sp3 hybridization by taking CONH3 6 times 3 plus as an example. Here the central atom cobalt 3 plus as a ground state electronic configuration 3d6 4s0 4p0, and for the D2sp3 hybridization, the electrons, these 4 electrons are paired in the inner d subshell, thereby making 2 inner d orbitals free for hybridization. That's why the participating d orbitals are from 3d. However, in the case of COF6 3-, the participating d orbitals are from 4d. That's why the hybridization there marked as sp3d2. But here the participating d orbitals are from inner shell. That's why the hybridization is marked as D2sp3. I hope you got the difference between D2sp3 and sp3d2. Remember this point. In D2sp3 hybridization, the participating orbitals are from inner d orbitals. So, in sp3d2 hybridization, the participating d orbitals are outer d orbitals. That's the only difference. So, in CONH3 systems 2 plus, there are 6 vacant D2sp3 hybrid orbitals are there. To that, electrons are donated by 6 ammonia ligands, yielding the formation of CONH3 6 times 3 plus. This molecule is also having an octahedral geometry. Now, hybridization and geometry. The type of hybridization determines the geometry and bond angle of a molecule or ion. This is the correlation between hybridization and geometry. sp hybridization leads to linear geometry. sp2 hybridization leads to trigonal planar geometry. sp3 leads to tetrahedral geometry. sp3d hybridization leads to trigonal bipyramidal geometry, and sp3d2 hybridization leads to octahedral geometry. The type of hybridization determines the geometry and bond angles of the coordination compounds also. This is a correlation between hybridization and geometry in coordination complexes. sp hybridization, linear geometry, the example is AgNH3 twice plus ion. sp2 hybridization, trigonal planar geometry, example is CuCl4 2 minus ion. sp3 hybridization, yielding tetrahedral geometry, typical example is Zn NH3 4 times 2 plus ion. sp3d hybridization leads to trigonal bipyramidal geometry, typical example is FeCO 5 times. sp3d2 hybridization create octahedral geometry, typical example is COF6 3 minus ion. And D2 sp3 hybridization, where inner d orbitals are take part in hybridization. The geometry is same as sp3 d2 hybridization, that is octahedral geometry, and the typical example is CO NH3 6 times 2 plus. So hybridization has a close connection with the geometry. Hybridization determines the geometry in simple molecules and ions as well as in coordination complexes. Now, determination of hybridization from molecular formula. It is possible to calculate the hybridization of the central atom in simple molecules and ions if we know the molecular formula of the compound. This is the expression, this is the equation used for calculating hybridization from the molecular formula. Hybridization H is equal to half into V plus M minus A plus A. So, here there are several terms. V represents number of valence electrons around the central atom. M represents number of monovalent atoms around the central atom. C represents the cationic charge and A represents the anionic charge. We can illustrate it by taking some simple example. First of all, I am taking CH4 molecule as an example. Carbon atom is a central atom with 4 valence electrons and 4 monovalent hydrogen atoms. It is having no charge, so it is not a cation, it is not an anion. So you can apply this concept. V is equal to 4, M is equal to 4, cationic charge is equal to 0, anionic charge is equal to 0. So we can arrive at the hybridization. Hybridization is equal to half into V plus M minus C plus A, that is equal to half into 4 plus 4 minus 0 plus 0, that is equal to 4. 4 orbitals are take part in hybridization. That hybridization is nothing but sp3 hybridization. So we got the hybridization of CH4 molecule as sp3. There is another example for illustrating the hybridization is NO3 minus ion. Nitrogen is the central atom with the 5 valence electrons and no monovalent atoms. It is having an anionic charge of minus 1. We can use these substitutions in the major equation, that is V is equal to 5. Number of monovalent atoms is equal to 0 since oxygen is divalent. Cationic charge is equal to 0 since it is not a cation. But anionic charge is equal to 1 since the charge is NO3 minus. So on substitution we will get a hybridization by putting the values in this expression, half into V plus M minus A plus A. So you are getting hybridization is equal to half into 5 plus 0 minus 0 plus 1, that is equal to 3. 3 orbitals are take part in hybridization, that is nothing but sp2 hybridization. So it is very well clear that NO3 minus ion depict sp2 hybridization. That all about the present module. Have a nice learning experience. Thank you.